The Heighway Dragon was discovered by NASA physicist John Heighway in 1966. In this video, we will explore several of the properties of the components that make up the Heighway Dragon, and which were first described in a 2003 paper. In that paper, it was shown that the Heighway Dragon is a countable union of closed geometrically similar disk-like planar sets, any two of which intersect at no more than one cut point. The construction of the dragon starts with a horizontal line segment. For the first iteration, scale the line by 1/√2 while rotating by 45 degrees. Then rotate a copy of this new segment by 90 degrees. Now repeat the scaling and rotation process for the second iteration. Continue this construction indefinitely, each time scaling the current figure by 1/√2 while rotating by 45 degrees, then rotating a copy by 90 degrees to get the next iteration. As the number of iterations increases, notice how squares begin to form. You can also begin to see the components starting to take shape. These are the geometrically similar disk-like planar sets referred to in the earlier quote. The Heighway Dragon is the limit as the number of iterations goes to infinity. But we can never draw the actual dragon. All we can do is draw a good approximation using a finite number of iterations. This image shows the approximation of the dragon after 14 iterations. The dragon is divided into many components that have similar shapes. The central and largest component can be decomposed into the union of 4 smaller disjoint pieces. The first consists of a copy of the Heighway Dragon scaled by √2/4 and rotated by 45 degrees clockwise. Another copy of the Heighway Dragon is also scaled by √2/4 and rotated by 135 degrees counterclockwise. These two copies of the Heighway Dragon placed back to back form a fractal known as the twin dragon. The second piece is a copy of the central component scaled by 1/2 and rotated by 180 degrees. And the final two pieces are also copies of the central component, each scaled by 1/4. We can use these 4 pieces to find the area of the central component. Denote the area of the Heighway Dragon by the letter H, and the area of the central component by the letter C. The area of the central component can be written as the sum of the areas of the 4 individual pieces using the square of the scaling factors of each piece. So we can express C as the area of the twin dragon, which is twice the area of the dragon scaled by √2/4, plus the area of 1 copy of the central component scaled by 1/2, plus the area of 2 copies of the central component, each scaled by 1/4. This equation can now be simplified and solved for C, and the result will show that the area of the central component is 2/5 of the area of the Heighway Dragon. If the initial horizontal line segment used to construct the dragon has length L, then the area of the dragon is L²/2. The area of the central component would therefore be L²/5. Now what about the other components of the Heighway Dragon? The components to the left spiral away from the central component, with each component a copy of the previous component scaled by 1/√2 and rotated by 45 degrees. Thus all are geometrically similar. There are an infinite number of these spiraling components, but their sizes eventually become too small to see. The components to the right also spiral away from the central component, with one slight difference. The first component to the right is a copy of the central component scaled by 1/2 and rotated 180 degrees. But then each successive component is again a copy of the previous component scaled by 1/√2 and rotated by 45 degrees. As with the left spiral, there are an infinite number of these geometrically similar components. The right spiral is actually a copy of the spiral on the left, excluding the first component. If a copy of this spiral is rotated by 90 degrees, it will overlap the right spiral. This is due to how the dragon is constructed as illustrated earlier in this video. We can use these observations about the components to show another way to compute the area of the central component. Number the components that spiral to the left of the central component starting with 1, and number the equivalent components in the right spiral to match the left. Then component K is a copy of the central component scaled by the factor 1/√2, raised to the kth power. Now the area of the Heighway Dragon can be written as the sum of the area of the central component, plus the area of the first component to the left of the central component, plus the infinite sum of the areas of all the other spiraling components on the left and all the components on the right. This expression can be simplified since the infinite sum is a geometric series with common ratio 1/2. The terms on the right therefore reduce to just h equal to 5/2 c, and so c is equal to 2/5 h, which agrees with our previous result. The last observation is about how any two components intersect at no more than one cut point, as quoted earlier. If we zoom in on the central component and the component to the left, we can notice how in this approximation of the Heighway Dragon, each component consists of many small squares. However, at the transition from one component to the next, there are three line segments in the approximation that form a zigzag pattern that is not part of any square. As the number of iterations increases in the construction of the dragon, two things happen. First, the squares in the components become smaller and smaller until in the limit they completely fill the interior of each component. And second, the three zigzag segments that connect the components decrease in size until in the limit the two components will meet at a point called a cut point. If we now zoom out a bit, you can see the same zigzag pattern at each transition from one component to the next in the left spiral. We also see this pattern where the central component is connected to the first component on the right. And because the right spiral is a copy of the left spiral, the same zigzag pattern will repeat between each component in the right spiral. Once we zoom back out, we can see the cut points for the components of the Heighway Dragon. They lie on two logarithmic spirals that run through the dragon. They are called cut points because if one is removed, it will divide the dragon into two disconnected pieces. So that is why the Heighway Dragon is the countable union of its geometrically similar components, and why any two components will either be disjoint or will intersect at exactly one cut point.